I am Santhoshkumar, research scholar in the Department of Electrical and Electronics Engineering, National Institute of Technology, Karnataka, Surat. My research supervisor is Professor Kumar. The presentation is on the topic Performance Investigation of Mobile WiMAX Protocol for Aggregator and Electrical Vehicle Communication in Vehicle to Grid. The contents of the presentation are: Introduction. Vehicle to grid concept has become a reality due to the advancements in the power grid and recent developments in the electric vehicle technology. V2G is also considered as a distributed resource. V2G plays a prominent role in meeting the load demands. It can sell power to the grid or buy power from the grid. So that is how it is meeting the load demands. Usually the electrical vehicles are parked for 90 to 95% of the time. The V2G is economical, efficient and effective. The battery charge is very important. The battery of the electrical vehicle is very important. The state of the charge of the battery is very crucial. If the state of the charge of the battery is in between 20 to 95%, the battery life will be good and the performance of the battery will improve. If the state of the charge of the battery is in between 40 to 90%, then the vehicle can be connected to the grid to sell the power. If the battery charge, that is the state of the charge of the battery, is less than 20%, the battery should be charged. That is, the vehicle should draw power from the grid. So the state of the charge is dictating the terms whether to sell the power to the grid or buy power from the grid. In case of vehicle to grid communication, we come across three components: the grid control center GCC, the aggregator and the electrical vehicle. The grid control center to aggregator and aggregator to EV. So aggregator acts as interface between a grid control center and the electrical vehicle. Aggregator will send the information to the electrical vehicles. The responsibility of aggregator is to mobilize the vehicles and bring it to the charging station. The grid control center will send the information about the electricity requirements to the aggregator. The aggregator in turn communicates to the EVs. It will invite electric vehicles and it will invite them to sell power to the grid. So aggregator will send the messages to the vehicles whether they are in motion or they are parked in a parking station. The components of the V2G are listed here. The figure shows the components of the V2G. So this is an electrical vehicle. This is the grid. This is the smart meter. The electrical vehicle is connected to this grid. Either the electrical vehicle can sell power, that is V2G, or it can draw power from the grid. Smart meter is the one which is communicating to the electrical vehicle. So the bidirectional way of communication is possible with respect to this smart meter, and it is communicating to this particular electrical vehicle. The vehicle can be connected to the charging locations, either home, apartment, garage, commercial buildings, station, etc. So this is the complete picture of vehicle being connected to the grid and the components, the aggregator and the ISO. So this is the picture of a V2G, or like vehicle connected to the grid. The system model of V2G. Here, as already you discussed, there are three important things in case of V2G communication: the smart grid control center, the aggregator and the electrical vehicle. The information should be broadcasted from this grid control center to the aggregator using the wireless network, and from the aggregator to the EVs using the wireless communication protocol. So the information from this end to this end and the information from this end to this end should be wireless. So in our presentation, we are concentrating on this particular concept. We are thinking of communicating from aggregator to the vehicle in a wireless way. So role of ICT. ICT plays a key role in communication. GCC, that is grid control center to aggregator, and aggregator to EV communication is very crucial. Communication is required for smart charging and discharging. So before getting into the details of path loss models, basically we investigate the path loss models once we are working out for the wireless communication protocols. So information, if it is being propagated, the signals which are being propagated will come across a lot of obstacles. Due to that obstacles, the signal gets faded. That is called as fading. So in order to work out for the fading and the loss in the strength of the signal, we work out for the path loss models. The path loss models calculate the electrical field strength and predict the path loss. And this prediction of the path loss is very important in planning the wireless network. The information is propagated by means of electromagnetic waves. The signals come across a lot of obstacles in the environment which causes path loss, as discussed earlier. So difference between the transmitted power and the received power is measured in decibels, is called as path loss. So the path loss is an important factor while deciding or planning the wireless network. So the path loss is categorized into three parts: the deterministic, empirical and stochastic. Deterministic is site specific. It is dependent on the geographical location of the environment, whereas empirical is based on the measurements. At the same time, it is based on the antenna height, distance and the frequency. Stochastic process use series of random variables to model the environment. So we usually work on the empirical models, and basically we use these empirical models to model the path losses, to work out for the path loss models. So these are the path loss models which we have got in our study, or which we have simulated, wherein we have analyzed and compared with the help of simulation results. The free space path loss is the ideal or realistic model. That is the one which will be always taken in order to compare it with the other models. The COS 231 ATA model is well suitable for urban areas, and it is for the frequencies 1500 MHz to the 2000 MHz. Then Stanford University interim SUI model is developed by the Stanford University, and it is a de facto standard of IEEE WiMAX. Then Hatao-Kumara is most extensively used for the frequency greater than 3 GHz. Then COS 231 WI model is suitable for the environment wherein the buildings are uniform. Ericsson model is also suitable for the urban areas. So the empirical formulas are picked for the simulation purpose, and we have compared using these empirical formulas. Then after working out for the path loss models, we have to think of the concepts of wireless connectivity, wireless communication. What all things have been already addressed in case of wireless communication for a vehicle to grid when it is connected to the smart grid, V2G when it is connected to the smart grid. Many researchers have worked on Bluetooth for V2G connection to the smart grid. Researchers have also investigated the Zigbee protocol. They have worked out for the Wi-Fi. The fixed WiMAX is applied to the grid control center and the aggregator. And in our work, we thought of working for the aggregator and we thought of working for the communication protocol which will address the aggregator and the EV communication. So we thought of taking into account the mobile WiMAX, which is well suitable for our application for the communication between the aggregator and the electrical vehicle. The WiMAX standard defines air interface for the frequency range 2 to 6 GHz. The ideal characteristics are it supports 50 km coverage area and data flow up to 70 megabits per second. So this is the ideal characteristic of a WiMAX, but in practice the coverage area is 5 to 7 km and 7 megabits per second. So this sounds reasonably good for our application, as the aggregator and the electrical vehicle, they will be placed either within the radius of 5 kilometers or within the radius of 7 kilometers. So the range is 5 to 7 kilometers. So we are working with the 5 to 7 kilometer and the 7 megabits per second. That's the mobile WiMAX. This is the basic block diagram of our mobile WiMAX. This is the transmitter, this is the channel, this is the receiver. So transmitter, the receiver and the channel. Communication channel is very crucial in order to address the issues with respect to communication channel, we had to work out for the noise related environments and had to solve so many, like we need to address a lot of issues here also in case of communication channel. So we have worked on the basic mobile WiMAX model. So this is the digital transmission process wherein we come across the bits are transformed or converted to symbols, symbols are converted to pulses, pulses are being propagated, pulses are converted to symbols, and symbols back to bits. So if you look at bits to symbols, it's a discrete domain, and symbols to bits, it's a discrete domain. The transfer of the information through the channel, that is continuous time. So this is the one wherein digital transmission process takes place. The source of information is this, the destination is the information which is received as the destination is this. So we are going to evaluate, like check out whether the errors have been introduced in this particular bits. So functional stages of WiMAX. This is the frequency domain and this is the time domain. If I go for IFFT, then the frequency domain components will be converted to or transformed to the time domain. We analyze the signals in the time domain. So this is the basic functional stage of a WiMAX, and these blocks are used in the WiMAX program. This is a basic OFDM symbol. The cyclic prefix are the P symbols which are repeated here. So this will help us to rule out the inter-symbol interference which will occur. So there are block of N data symbols, there are P symbols. So every frame what we take, it will have this kind of repeated P symbols. The OFDM symbol has three things: the data for data carriers or transferring the data, the pilots for keeping track or estimating the channel, and synchronization. So channel tracking, estimation and synchronization can be done using these pilots. The guard bands are used to provide frequency guards between the, like they are used to safeguard the symbol. That is, we are going to work out for reducing that ISI using those kind of bits, guard bits. Multipath caused by reflection. So if you look at the transmitter here, there is a mobile, the information which is transmitted directly, and you can look at the other signal which is wherein it is coming across the obstacle, it is reflected back and receiving the mobile, like it is reaching the mobile, and at the same time it is reflected by the vehicle. So this is alright, but these are the ones which will create a problem. So that is called as multipath fading. So it has to traverse through the multipaths. So multipath induced time delays. Here, if it is a direct thing, the signal will reach here. But if it is through these multipaths, the signal will reach here. So the time which is responsible for this will induce the ISIs. So this is not accepted. So it is inter-symbol interference. Now, frequency selective fading, the signal bandwidth, there are large deep fades in this signal bandwidth. So this is due to the multipath distortion. In order to address this, we come across the OFDM or OFDMA. So mobile WiMAX is based on OFDMA. OFDMA allows for sub-channelization of data in both uplink and downlink. Sub-channels are just subsets of the radial carriers. They can use contiguous or randomly allocated frequencies. Now, OFDM symbol period. This is the symbol period. This is the cyclic prefix symbol period, cyclic prefix symbol period. So one thing we need to notice here, that the symbol period, longer symbol period and the cyclic prefix will rule out the ISI. So it will eliminate the ISI. Whereas in case of single carrier, the delay induced by multipath can cause the symbol received along a delayed path to bleed into the subsequent symbols. It is bleeding into. So this is how the OFDM is eliminating ISI, and the cyclic prefix and the FFT period are the two components of the OFDM symbol. So this is the IEEE 802.16 for range equal to 256. There are three things: data, pilots and nulls. The data is being sent. So IFT, FFT, here the frequency domain. After this we get the signals in the time domain. That is a transformation from the frequency domain to the time domain. So x of k to x of n plus of n. Now, the concept of path loss, we have gone through the concept of Ymax, how Ymax can be used for aggregator and electrical communication. Now, in the case of simulation, we have considered these parameters for simulation. The distance between the aggregator and the EV. Now, aggregator acts as a transmitter, the EV acts as a receiver, the distance between them is 5 kilometers, and the transmitter height is 30, the receiver antenna height is either 6 kilometers or 10 kilometers. We have simulated for both the cases 6 and 10. And the base transmitted mobile transmitted power is 30 decibels per. Now, this shows the simulation results of all the path loss models which we have considered for our application. Here, in case of free space path loss, you can observe one thing. It is demonstrating 118 decibels path loss. So this is the idealistic model. But we are concerned about these path loss models. Here, if you look at this particular line, is a SUI. It is sounding reasonably good. But at the same time, if you look at the Ericsson model here, the Ericsson model is also working hand in hand as the distance increases. Sometimes it is better as compared to the SUI. So we can conclude that SUI and Ericsson work hand in hand as the distance increases. And if you look at these two curves, the cost theta and cost WI, these two curves are demonstrating almost equal path loss till this particular point, and as the distance increases, there is some difference. So it is observed to be around 165 to 167 decibels. At the same time, if you observe this particular curve ECC 31, it is falling in these two limits. It is said to be moderate. The path loss demonstrated by ECC 31 is moderate, and the path loss obtained by SUI and Ericsson is considerable. And the path loss obtained by cost theta and cost WI are higher as compared to these two things. So this will show us the path loss in decibels and the distance between the aggregator and EV in kilometer. The signal, if it is propagated from transmitter, that is aggregator, and if it is sent to the electrical vehicle, the signal should not get faded and there should not be any path loss in our area of interest. So we are interested in that, where actually the path loss occurs and how the information is, like the signal is faded. That is what we are investigating. So these, say, we have gone through these path losses, and when it comes to V2G, we consider one thing. V2G, the vehicles may be parked either in a basement area or vehicles may be parked in urban area. So we consider two cases, urban and suburban. If they are parked in base station or basement, maybe signal reaching there will have the difficulties. So we have to work out for the non-line of sight. Okay. So many things have been investigated. So the path loss models for V2G in particular have been, like, we can consider these two things, that is SUI and the Ericsson. The path loss models for at 3 km distance. If you look at 3 km distance for the 6 meter antenna height and 10 meter antenna height, this is same and this is same. If you look at, there are two strong contenders. So 144 and 105 in the sense SUI and Ericsson. Here also, if you look at the SUI and Ericsson for 10 meter receiver antenna height and the 6 meter receiver antenna height. For the 3 km distance for the suburban regions, once again, if you look at the suburban regions, the SUI will sound very good as compared to the other models. So that is why SUI is considered the de facto standard of IEEE 802.16. So SUI has been separately simulated for the three terrain regions, type A, type B and type C. And if you look at the path loss versus the distance, you can observe that the path loss things have been already simulated, and SUI, this is chosen from RXC model, so this model is used for Ymax. After going to the path loss, we thought of working with the mobile Ymax. The Ymax protocol was considered, And here we thought of working with the BR versus SNR. To attain this particular bit error rate, we thought of having